of one of the most interesting European funded projects related to the implementation of platforms to support energy applications. And Alberto Dognini from the University of Aachen, from RWTH in Aachen, will be our speaker. Very quickly, who your host is today. We are Ideasforum, Innovation Hub, an aggregation, a spontaneous aggregation of organizations in the public and private sector and of individuals that are working to somehow find ways to support the digital transformation of civil society by leveraging on the approach of open source. So by introducing the open source culture in the way we don't do only technology, but also we look at governance models, business models, and so on. We are definitely driven by a push to work together. So we want all of our events and all of our activities to be fostering cooperation between different entities that are, I would say, the vibrant part of our society. We strongly believe in diversity from any angle or any angle you want to look at it. So we don't care about what kind of open source community is somehow providing something that works. But we try to make it work with the other successful efforts of others. And for sure, we'll love to entertain you and love to talk about topics, but we are also heavily engaged in building the infrastructure and the environment for people to be able to test the applications that they are developing. One of our key areas of expertise is the one that we will be addressing today. Smart Energy. We are hosting several of the members of the Mission Support Committee on Smart Energy, and this is definitely giving us a boost and a push in this domain, but we are also focused on what is usually called smart cities, so the digitalization of public services and public infrastructure, smart mobility, and also that part of the open source activities of the European Commission that falls under the Connecting Euro Facility digital program umbrella. And we are looking at how e-government projects can be supported by those tools. We, as I said already before, are tightly engaged with the work of the Fiware Foundation, and we have one of the Fiware IAPs, one of the two in Germany, and one of the many spread across the globe. And as I said, there is a number of different entities, as you can see, cities, universities, open source communities and programs, and a number of, I would say, relevant industry players that are working with us, supporting us, and supporting our members. I will stop here and introduce our guest today, Alberto Dognini. Alberto, whenever you want, take control of the presentation. I will stop sharing and the ball is with you.
Yeah, thank you very much, Gianluca, for the introduction, and good afternoon, everybody. Let me just share the screen. So now in the presentation mode, right?
Correct. You're good to go.
Okay. Good afternoon, everybody. As Gianluca just introduced to the I can present the Fismep project. Fismep is an European project which was funded by the framework ERANET, Smart Grid Plus, under the Horizon 2020. And as the title says, so Fiware for Smart Energy Platform, we are directly based on Fiware, which is one of the pillars of Ideasforum, as we have just seen. Fismep is a project that lasted 3 years and just finished on last Monday. So in the meeting on today, I can present you which were our achievements that we have done and the ideas that we had in mind. First of all, I want to start with an overview on which is our consortiums and our trials. So the main idea of Fismep is to develop a platform that can demonstrate the use of Fiware for the smart energy. There was already a project in the past that tried to demonstrate and implement this. We wanted to go beyond and to use Fiware for additional use cases. So in particular, there are 3 trials that we have developed in Sweden, in Romania, and Germany. And these 3 trials are quite different each other. In the first 2, Sweden, we were integrating the building energy management system, also with the involvement of the users that are living in the buildings for the energy consumption. For the second trial, which was based in Romania, the idea was to monitor and control the transmission grids via the phasor measurement unit, which is a device that I can specify and give some details a bit more later. And the third one is the trial in Germany, where I was based with the RWTH Aachen University. And it consisted of the automation of the distribution electrical networks. All these 3 trials were referring to the same Fismep platform that, as we said, is based on the Fiware components. We were using one of the main self-building block of Fiware, which is the Orion Context Broker. And yes, these 3 trials were sharing the same components in order to achieve their respective use cases. Before going into deep of each trial test, I want to give you a general overview of the platform and which is the idea that we had in mind for their implementation. I just want to, yes, this can be useful. First of all, the architecture structure that we have in mind. It is definitely based on 3 layers. And it is defined according to the service-oriented architecture. So what we have in mind is the algorithm that we want to use with this platform, or the final goal that we want to achieve. These 3 layers are visible in the picture that we have here on the right. The first layer here is responsible for the interface with the field devices. So it's this yellow part, and it's related to the acquisition of data from the sensors that we can have in the building or we can have in our transmission grid. And moreover, is also related to the data model that we have to convert, or maybe we have to adapt to the internal building blocks that we have. The second layer is related to the specific software components. Some of them are taken by Fiware catalog. Some of them are developed by us during the project. And these specific blocks are responsible for the acquisition of the data, for storing in the time series databases, or to apply the specific energy algorithm. And the third layer is the Open API as a backend access to the data that we have. Going a bit more into deep of the structure of the architecture, we have this picture that shows somehow the different layers according to the components that we have used. The components with the yellow color are related to the first layer, so with the interface to the field, and they can make use of the direct communication platform with the HTTP or by using an MQTT broker. We have the so-called IoT devices, so Internet of Things device that can communicate and provide the streams of data. And on the other side, the corresponding component in the platform is represented by the IoT agent, which is a component of the Fiware catalog that receives this data. Here in green, we can see the components of the second layer. And the central one, which is the core of all the Fiware applications, is the Orion Context Broker here. That is managing the data that has been received and is responsible for the implementation in the time series databases, as it can be the created B, the one that we have used. On the left side, then we have the specific services that we are implementing in our specific field test. For example, in my field test in Germany, we were developing the service restoration for the distribution grids, and I will talk later more in detail about this. Another thing to mention is the role of the NGSI, the so-called next generation of service interface, which is a de facto standard that is used inside the Fiware component for the publish and subscribes of all the data that we have. The NGSI, going a bit more into deeper, is based on entities. These entities are referring to physical objects like the sensors or the actuators that we have in the field. Sorry, I was hearing some noise, but I don't know if everything is fine or what. Okay.
Yeah, we can hear you well, don't worry.
Okay. I think someone has the microphone on. By the way, yeah, we have these entities that are related to physical objects in the field that can be sensors or actuators, or they can be related also to the software components that we have. And each entity is specified by an ID to identify it, and several attributes, which can be static or dynamic. Each attribute is defined by its name, the type, and the value of the attribute. If we want to define the relationships of these entities in a semantic way, so making use of the ontology concept, we can also specify the metadata of each entity. The last aspect that I want to specify about the platform is related to the IoT agent. As I said before, the IoT agent is a component of the first layer, so the interface to the field. It's a Fiware component of its catalog, and it is divided into two parts. The IoT backend, which is responsible for the connection and the management of the devices in the field. So it manages the authorization and the authentication of the devices. And then we have the IoT gateway, which is responsible for the protocol interface, so to define the data models that are acquired and eventually also to adapt to the ones that are acquired in the platform. Now this overview of the platform is concluded, and I want to go into deep of the specific field tests that we have. The first one is the field test in Sweden. As I initially said, it is related to the building energy automation systems. So the idea is to make use of two apps that we have and to make them interface each other. One of the first tool is the Aero app, and the second one is the CISO platform. The Aero app basically is an app that is working on the mobile phone, and it is used by the residents of one of our living lab in the Chalmers University that is located in Gothenburg in Sweden. And these residents uses this app to specify the forecasts about the consumptions of electricity or heating, and to get back some recommendation about, for example, which is the best time to adapt it, or how are the tips to reduce the footprint or increase the reliability and their consumption. These data that are exchanged with the people that are really living in this building are provided to the CISO platform, that is a platform used by the E.ON grid, so the company that is responsible not only for the electricity, but also for the heating and the cooling at the district level. And with the forecast that is received from the users, they can better plan their production or the electricity streams and power flows. Here in this slide, we can see more in details which are the different components of the Swedish field test. So, for example, this was the living lab that I anticipated before, in which we have the different blocks and different streams. And on the other side, the field test was related also at the district level to the city of Malmö. The data that were received, as I said, from the users that were living in these buildings were provided to the Hero app and then exchanged via the Fiware components to the E.ON platform, which is the CISO platform. Another aspect of this field test is the monitoring of the building of the RWTH Aachen University. In this project, Aachen was responsible for developing the Fiware components and for using and interconnecting them with the controllers. And what has been done is to directly use the Fiware platform to automatically control, for example, the temperature in our building according to the sets of the users. Now I want to move to the next field test, which is the Romanian field test. As I anticipated, it is related to the monitoring of the transmission grids in different locations in Romania, and it makes use of the phasor measurement units. The phasor measurement units are devices that basically are collecting measurements of the electrical quantities, as can be the frequency, the voltage, and the current. And it is referring these quantities to a common reference of time, which is given by the GPS. And using these devices in different locations of the grid, you can synchronize each other the different measurements that are collected. One example of the PMU, for example, is visible here in this picture. And in particular, the data that are provided and collected are the frequency, the rate of change of frequency, so the variation of the frequency in the grid, the different components of the voltage for the different phases, and the ones of the current. Here is the representation of how the data are integrated with the platform. So each PMU is communicated to an open PDC, phasor data concentrator, and then via the IoT agent, it is provided to a time series database, and then to the Orion context broker for the monitoring and visualization. In this sense, the Romanian partners developed a front-end web app for the different evaluation of the PMUs that they have and the specific electrical quantities that they measure. Or they make use also of the Grafana component, which is related to the Fiware catalog. For example, selecting two different PMUs, we can evaluate the comparison of their frequency that they are monitoring. And yeah, there are different thresholds that in case they are hit, they can provide alarms or inform about corrective actions that need to be carried out. Now I want to move to the German field test, which it's occupying most of this presentation, because I will give you more details about what I personally did together with my colleagues in RVTA. And as I anticipated at the beginning, it is related to the automation of the distribution grids, in particular in medium voltage. The starting point is given by the ongoing transformation of the electrical power system. In particular, the more and more presence of the IoT devices. So all the electrical actors nowadays are able or will be soon able to provide data in real times about their consumption, their forecasts, and on the other side, they are also able to receive commands and actuate the physical changes and adapt to the situation that is varying in the grid. So this is all part of the so-called smart grid automation, but this needs a continuous monitoring and an analysis of a so huge amount of collected data that needs to be received in a very great streams of data. And this so huge amount of quantity needs also high computing power and time-consuming algorithms. This means that we have to face these difficulties, for example, by making use of the cloud architectures and using the distributed system services. So these are specific energy services that are independent of the grid topology or the specific number of items that we have, but they can adapt on the data that are received, and these are called middleware because they are independent of the specific application. In this way, we have standard APIs and protocols. So the goal of the German field test is to deploy the platform, which is specifically tailored for the management of the power distribution grids. This is based on Fiware technology, and what we want to achieve and what we have done, and I'm gonna show you now, is the monitoring of the medium voltage DC grid. And then I will concentrate a bit more on the service restoration in case of faults on the grid, which has been developed as a middleware in the platform. Yeah, this is related also to the reconfiguration of the network. And as test benches or trials, we made use of the FEN research grid, which is a grid that we have in our campus of the university, or a grid model for the simulation of the faults, in particular using the real-time digital simulator and the standard automation protocol, which is the 6150. In the end, I will also show you how we emulate in a demonstrator the achievements that we have reached. Yeah, first of all, the monitoring of the medium voltage DC grid. As I said, we have a research grid in our campus, which has been built with a national project. And this is a scheme of the medium voltage part. In particular, we have 3 different buildings, which are interconnected by 5 kilometers cables. The cables are at 5 kilovolt in DC. So each pole is a plus minus 2.5 kilovolt. And in each of these locations, there is also the low voltage side, which is managed in DC or in AC. And we have different power converters, which can be readapted each other in order to have different configuration of the AC-DC system. And this has been done in order to test the DC technology that we can have and the viability of the AC-DC systems, like a new advancement for a new level of the future distribution grids. What we wanted to do in the Fismep project is to validate the monitoring of this grid using the Fiware components. So we have different measuring points, which can be inside the power converter or at the point of common coupling or directly on the cables in the switch gears. And we took these measurements as a virtualization into the cloud platform. For example, what we see here is a zoom of one of the buildings that we have. In particular, here we have a system of double bus bars and 3 different power converters that are connected in this point, which can be rearranged by commanding these switches. And here is a zoom of one of the panel that we have. In particular, we have the different disconnectors. We have the transducers that are the sensors that are measuring the current and the voltage that we want to virtualize with Fiware. And these analog measurements are collected by the ID, so the Intelligent Electronic Device. What we're going to do is to interface this Intelligent Electronic Device with our Fiware platform. We made the use of a Villas node, which is a tool developed by in our institute, and it is responsible for the data model adaptation and the protocol translation. In this way, we can digitalize the data that we have received and translate into the MQTT protocol and make use of the standard automation protocol for the power systems. Using the IoT agent, we can communicate with the Orion context broker, which is centrally managing all the stream of data that are coming, storing in a time series database and visualize in Grafana. The monitoring of the distribution grid is carried out by setting thresholds that can raise awareness to the grid operator or initiate some corrective actions in the grid. For example, what you see here is the monitoring of the voltage and current in case of a change of a load that we have operated on the grid with a decrease of current and consequently an increase of the same current. This was the first part of the German trial site, which was related to the monitoring of the medium voltage DC grid. And now I move to the second use case, which is related to the service restoration. First of all, I want to introduce what is the service restoration. And we have to start from the picture that we have here on the right side, which is simply showing 2 feeders that are managed in medium voltage. These are related to 2 different substations. This is one feeder and this is the other. And the black square is the closed circuit breaker, and the white square is the normally open circuit breaker, which means that these 2 feeders are electrically disconnected. Each point that we have here is a load that we have in the electrical grid. So the point is that in case, unfortunate case of a fault that occurs in the grid, we have to isolate this fault by opening the upstream circuit breaker, the upstream switch, and opening the downstream switch. In this way, we have isolated the fault, but consequently, the loads that are downstream are now de-energized, so they are not connected anymore. They don't receive energy anymore. What we have to do is to close what we call the tie switch, so the normally open switch, which is at the middle. And in this way, we can energize the loads from the other side, from the other feeder. And this operation traditionally was carried out by the operators, which were driving directly on the fault location, identifying the position, and manually opening or closing the switches. But what we can do nowadays is to automate the whole process with the distribution management system. And in this way, we can carry out in a minimum time with the so-called fault location, isolation, and service restoration, which synthesizes all the phases of this process. And what we reach is a prompt intervention of the protection and minimization of the risks for the people, and also a minimization of the consequences to the devices that are experiencing an overvoltage and overcurrent. And this increase of reliability for the grid is quantified by, in particular, I reported here 2 indexes. The first is SIDI, which is an average of the duration of the faults, of the outages in 1 year, and the second one is the KIDI, which is considering the number of customers that we have in the grid. Now, a bit more the situation by considering a larger grid, which is no more constituted by 2 feeders, but more feeders. We have 4 substations, but the common denominator is that this grid is managed as a radial. So again, we have the normally open switches, which are the white squares, so that the different substations are electrically disconnected. In case we have a fault in one of the points of the grid, again, we have to open the surrounding switches to isolate the fault. And consequently, we have some loads that are now disconnected, de-energized. So what we have to do is to find a way to initially, we have to determine which is the most critical load. And this is done by considering the nature of this load, of these specific points. In particular, we analyze if there are critical components like a hospital, transportation sites, or data centers, for example. And once we have identified the most critical load, we can find all the possible candidates, so all the possible alternative paths to reconnect it. For example, we can reconnect from the substation 3 by closing the switch 10, or we can close from the substation 2 by closing the switch 7. And yeah, these 2 paths are found because they are the shortest electrical path. In particular, are the path with the minimum impedance, so with the lower losses. But among these 2 paths, which is the best one, we have to determine with the service restoration algorithm. So what we can do is to consider the measurements that we have from the field, the voltage and current measurement, the power measurements. We consider this measurement with the weighted least square approach, which means that the measurements that are more accurate have more importance in the determination of the final state. And what we do is to forecast how it will be the grid in case we apply one of the candidates. For example, here, in case we close the switch 10, how will be the power losses, how will be the current level, and the voltages. So for each candidate, once we forecast how will be the situation, in case we apply it, we have to verify 3 constraints. The first one is the radiality, as I said at the beginning, so that the feeders are electrically disconnected each other. The second is the voltage limit. And the third is the loading limit, so the amount of current that is flowing in each line. In case these constraints cannot be respected, we can stand for a temporary emergency condition in a limited period of time. And among the different candidates, the ones that satisfy the constraints, we have to evaluate which is the best one according to different criteria. The first one is to minimize the power losses, and the second one is the utilization of the electrical lines. So how much the current that is flowing in an electrical line is far from the maximum value of current that is admissible. So indeed, if here we are recording the 3 minimum values, we have 4 parameters. Okay. Since we have 4 parameters to define one final solution, we have to use the multiple criteria decision analysis, because we have indeed the 4 criteria to base our final decision. And this MCDA method is based in 2 parts. The first one is the AHP, analytical hierarchy process, for which we consider the comparison among the couples of criteria. So in this matrix, for example, here, we compare P and theta 1. Here we will compare P and theta 2, and so on. And the grid operator will assign an importance which is more important among P and theta 1. In this way, we pass from the comparison among 4 criteria to the comparison among 2 criteria, which is easier to be faced. And the second part, which is the TOPSIS, defines which is the ideally good solution and the ideally negative solution, and measure each candidate from these 2 positive and negative ideally solutions. So the best one, the solution that is closer to the positive one, it is chosen for the final implementation. This is the final test setup that we have used. So we have simulated the grid with our real-time digital simulator, which is able to interface with communication cards with our Fismep platform. On the other side, it is also able to communicate with the medium voltage protection relays, which are the industrial devices that we have in the field. In our test laboratory, we inject the overcurrent into the relays, which then trips because they detect the fault. They communicate with the standard communication protocol that a fault occurred, so they open the respective switches in the grid. On the other side, the data are continuously set as data streams to the Orion context broker. This component in the platform receives continuously the data from the simulated networks. When it detects that a fault occurred, it informs and initiates the service restoration middlewares, which retrieves the most actual data set. It computes the solution and sends it back for the actuation of closing commands to the simulator to close the switches according to the candidate that has been computed here. And this process repeats until all the loads have been restored. Here I just want to show you again the different tests that we have carried out. So in this one, we only consider the minimization of the power losses in the grid. And we start again from the fault in this location, and this green circle that represent the load that are without the energy, that are de-energized, and we want to reconnect. So as we want to reconnect this B1, the service restoration computes that this is the best candidate solution, because in this way, among the different candidates, is the one with the lower power losses. In case we have closed this switch and a second fault occurs, we have again to isolate by opening the neighbor switches. We have an additional set of loads that are now disconnected. And there is only one way to reconnect these loads, which is via closing this switch, because it's the only one that is connected to these loads. Now, the last group of loads that need to be reconnected are these ones. And they can only be reconnected by the switch 6. In this way, we have we reach the limit of the maximum current that can flow, and so we are in an emergency condition that can last only a limited amount of hours. In the second test case, we didn't consider only the power losses, but also the utilization of the electrical lines with the parameter theta that I explained before. And in case we have a fault here and these de-energized loads, we can reconnect them by closing the switch 6, 7, or 8. If we give much more importance to the utilization of the electrical lines, and we don't give importance to the power losses, the best solution is via this switch. In case we also consider the power losses, so in the case 2B, for the final solution, we close the switch 8, as we see here. In the last assessment case, we considered a larger test grid, which is composed of not only 40 nodes, but 400. Basically, we took a specific subgrid block and continuously connected to our original model in order to reach 400 blocks. And what we want to measure is the latency time for the process that we have. In order to do it, we repeated each test 50 times with our simulator. And at the beginning, we wanted to see the latency between the occurrence of a fault and the activation of the algorithm, the activation of the service. And in case the grid is 40 nodes, we measured 0.1 seconds. And in case the grid is composed by 400 nodes, it increases to 1.3 seconds. And we have compared this data with the data that are present in the literature, in particular the latency between the remote terminal units and the control centers of the grid operators, and this is in line with the results that we have obtained. As a second verification, we wanted to check the computation time of the algorithm itself. So in case of the 40 nodes grid, we found an average of 5 seconds, and in case of 400 grids, we found an average of 86 seconds. Again, we have compared this value with the literature data and the reports of the grid operators in Europe, and it is compatible with the solutions that we have for the automatic self-healing freezer, which is in average 3 minutes. And of course, we have also compared with the data of the reports of the grid operators, which are not automatized yet. And so nowadays, the value, for example, in Germany, in 2016, so the last report that is available to us, was corresponding to 40 minutes. So we have a great improvement of the duration of the reconnection for the disconnected loads. Last point that I want to show you is the Fismep demonstrator. So the concepts of the different distribution grid management has been realized in a physical demonstrator, which is composed by 3 different parts. The first one is the grid. So the branches that we can see here that are not only mechanically interconnecting the different nodes, but they are also electrically connecting them. So they are also favoring the exchange of real power and real energy. And then we have the different entities, which are related, for example, to prosumers or consumers or renewable energy sources like the wind turbines or the solar panels. And each entity has its own specific properties. For example, they show how much power they are producing. You can change the value of the wind and so change the power that is produced. And they interface each other and balance the power flow. On the other side, we have also the upper Fiware platform, which is receiving this data from the entities via the MQTT over the Wi-Fi, because each entity communicates via Wi-Fi. And in the platform, we have again the IoT agent to receive the data, which are managed by the context broker, stored in the MongoDB, and then the specific services to manage the energy consumption. Just to conclude, I want to say our impression about these implementations is that Fiware helped us to concentrate on the specific energy algorithm, and we had only to take these software components from the Fiware catalog and to make use of the cloud-based properties. And as next steps, we want to continue the development of additional energy services. So not only the service restoration, but also the reconfiguration without defaults, for example, or for different kind of grids. And on the other side, we are implementing the achievements and the results in a new project. For example, Hyperride is a new project from Horizon 2020 that is evaluating and testing the AC/DC technology. And OpenDI, which is a coordination and support action that deals with the data exchange and the platform's implementations. This is the conclusion of my presentation, and now I'm happy to take your questions and reply.
Thank you, Alberto. I have a question for you. Is not, I would say, properly technical. It's, I would say, more business oriented. When you look at the new directive on so the directive 941, I think, of 2019, and at the role of local energy communities, what do you think is the role, or could be the role, of platforms like Fismep in supporting this kind of projects?
I do think that what Fismep has shown is that there is a way to ease the integration of the energy components that we have. So if we have to think about for example, local energy community, that they don't have to start from zero to develop again something to integrate their devices, but they have a reference. So they have an example of how Fiware can help in collecting their data. And they have a proof that the energy automation services can be reached and can be achieved also a larger scale, and not only in this limited number of trial tests that we have. And yes, this is what I do think for the.
What do you think could be, I call it a next step for Fismep? Is there already any activities focused in or on leveraging on the achievement of the project?
Okay.
You were mentioning the reuse in some other initiatives, if I'm not mistaken.
Yes, exactly. So I have in mind the two directions of the next continuation of the achievements that we did. One of them is about the integration of the 5G technology. The Fiware has already been tested in one of our projects, which was called N5G Hub, National 5G Hub. And now we are starting as Institute a new project, which is N5G Hub 2, in integrating Fiware with the 5G for the energy components. On the other side, Hyperride, which is the project on the DC technology, is integrating in the Fismep platform. So based on
It looks like we have lost Alberto. Well, unfortunately, it looks like his connection has been interrupted. Let me then, considering that we are close to the end of the time that we had allocated to this webinar, let me somehow thank Alberto. We will have to reach him anyhow outside. And I want to thank you for attending his presentation and the sharing of information with reference to Fismep, so to these initiatives to leverage an open source to start building the foundation. Alberto, yeah, I was closing because unfortunately
I lost the connection. Yeah,
anything else you wanted to add?
I can recap a bit because I don't remember. I don't know how long did you listen to my reply. What I wanted to say is that the achievements that we are using for the next phases are two projects in particular. One is the N5G Hub, so a project that is integrating a Fiware with the 5G technology. In particular for the building energy management system. And the other direction is, as I mentioned, the Hyperride. Hyperride is based on the DC technology. And what we want to do is to integrate into the Fismep platform, so integrate also with Fiware, aspects like the cybersecurity that was not so well analyzed in Fismep.
Okay, I think these are all relevant points, especially when we look at security, cybersecurity of basically microgrids, where you have application developed locally that needs to integrate with the grid and with the work of the TSOs and DSOs. Yeah. So this is definitely a topic that has not been addressed. It's not just an issue or a point that you want to build on. It's really a major concern because we will see hundreds, if not thousands, of local energy communities becoming part of the grid and the market. And this will definitely bring another epochal shift and another epochal change in the world the energy market operates, especially in support of the Green Deal, so the clean energy projects that we are all striving for to address climate change. Alberto, thank you. I just wanted to make some very brief closing remarks. I had started thanking you while you were not connected, and mentioning the fact that this is a very interesting example of how open source can come in support of energy application and the energy industry. We will next week have another event specifically dedicated to German developers, and we will be introducing the Linux Foundation for Energy program to a German audience. This is a first. I'm sorry if any of you doesn't speak German. But I mean, this is another interesting opportunity to have an understanding of how bottom-up project like Fismep can integrate with the top-down work that the Linux Foundation for Energy community is doing, and how the grids, the smart grid and or the smart grids and the microgrids can interact one with the other to build the energy of the future. The event next week will be our last for this year, and soon we will start communicating about the program for 2021. I hope I will be seeing you again. And I saw question popping up if there will be an English version of the LFE project. We'll probably have events in which we will have a representative of the LFE, so the Linux Foundation for Energy program, participate into Ideasforum and Fiware events. So there for sure will be opportunities to hear more about it in English. And then there is a number of events that the LFE is organizing, but we will try to share information about when you can participate or register for these events in the future. So I wanted to thank you for attending, for participating, and Ideasforum hopes that you will be staying in touch with us, eventually even help us and contribute to our work. And with this, I will end our day, thanking everybody and hoping that we will see you again soon. Have a nice day and see you soon. Bye-bye.
Thank you. Thank you, everybody. Thank you, Gianluca.
Thank you.
Bye-bye.